This lesson is focusing on trigonometric ratios. You may have heard that trigonometric ratios relate to triangles, and while this is true, it can be easier to interpret them using circles. Let's pretend you're in the middle of a dome about to hang a screen. So here's our dome. You point to some angle theta, and that's where the screen will hang. So this side here is going to be our screen height. The angle you point at determines the height of the screen, the distance to the screen on the ground, and then we have our radius of our circle. So the sine of theta can be written as sine theta, which is the height of our screen. And the cosine of theta can be written as cos theta, which is equal to the distance to the screen, which is from the ground. And lastly, we have our radius, which in this case is going to equal 1, which is equal to the distance to the top of the screen. So say you want the biggest screen possible. Say you're standing in the middle of our dome and you want the biggest screen possible. You're going to point straight up. So here you have the biggest screen possible, but it's right on top of you because you're in the middle. Say you want to have the smallest screen possible when you're in the middle. You'd point over to the edge. So here we wouldn't even have a height of the screen, but that's the smallest screen possible. So if you wanted the screen as far away as possible from where you are, it would be when you have the smallest screen. If you want the screen as close to you as possible, it's when you would have the biggest screen. So the height and the distance move in opposite directions. Bring the screen closer and it gets bigger. Move the screen away and it gets smaller. I'm now going to show you where trigonometric ratios, sine, cosine, and the tangent come from. So first off, let's have a look at sine. So we're going to imagine that sine theta is equal to the height of the screen. We are going to put the screen at various spots along our dome, starting from the furthest away position. And the height of the screen we will plot on this graph. When the screen is furthest away, the height is 0. So we're going to start at 0. The highest possible screen is equal to 1. So when our screen is at its highest point, that's going to be equal to 1, as that is the length of our radius. So starting from 0, as we increase the height of the screen, let's start at 0 and we're increasing the height of our screen. You can see that the change in height is increasing quite rapidly. So it's going from 0 to this height, and from this height to this height, this height to this height. And you can see that it's quite rapid. It's a rapid change. So when we look at our graph is going to increase rapidly as well. So starting from 0, we're going to shoot up. So now, as the screen gets closer to the maximum height, you can see that the change in height slows. So the height difference between this point and this point is less. So our maximum height is 1, so it's slowing down and it reaches its maximum height. So this is when height equals 1. Once the screen reaches its maximum height, it begins to slowly decrease in height. So between this point and this point, it's slowly decreasing. And we can represent that on our graph like that, slowly decreasing. So as the screen gets further away, the change in height starts to decrease rapidly until it reaches a height of 0. So it's going to rapidly decrease until it reaches 0. Now let's imagine we are hanging the screen underground. So we're going to draw our dome. Now we have a circle, there we go. So the height of this screen is increasing rapidly to start with. Increasing rapidly, but in the negative direction because it's going underground. So we're going to continue this line in a rapid increase, but it's negative. Now, as the screen gets closer to the maximum height, which in this case, the maximum height is -1. So let's add that to our graph, -1. The change in height begins to slow. So our graph begins to slowly reach -1. Once the screen reaches -1, it begins to slowly decrease in height. So you can see that the height of the screen between these 2 points and these 2 points is a slow decrease. So we can do this on our graph, so it's slowly decreasing. And then as the height of the screen approaches 0, it rapidly decreases. So the steepness of our graph rapidly decreases until we reach a height of 0 and 1 revolution is done. So this graph represents 1 revolution of our sine graph. So how do we compute this percentage of the height of the screen at any angle of theta? So what we can do is we can divide the current value of the height by the maximum value, which is the radius, and in this case, 1. So having a look at this here, we have our radius, which we said is 1. Then we have our height of the screen and our angle theta. So sine theta is equal to the height over the radius, which is 1 in this case. So the height of the screen is the furthest side from this angle. So we call this the opposite. This side is called the opposite. The longest side of the right angled triangle is called the hypotenuse. So we can rewrite our formula as sine theta is equal to the opposite side divided by the hypotenuse. So let's move on to our cosine. We are going to imagine that cosine theta is equal to the distance to the screen on the ground. So we are going to put the screen at various distances, starting from the most furthest away position on the ground, and we're going to plot that on this graph here. When the screen is the furthest away, the distance is 1, because that's our radius. So our starting position is going to be 1. So starting from 1, as we decrease the distance to the screen, you can see that the change in the distance is decreasing rather slowly. So if we're decreasing the distance, you can see the distance between this point and this point, and this point and this point, is changing quite slowly. So the start of our graph decreases slowly. Now as the distance of the screen gets closer to 0, and we know that distance is 0 when our screen is at its maximum value, we can see that the change in distance rapidly increases. So if you look at this point to this point to this point, the distance has rapidly changed. So on our graph, we can show that with a steep decrease. And we know that when our screen is at maximum height, it's 0 distance away. So that's why this is our 0. Once the screen reaches its minimum distance, it begins to rapidly increase, but as it's going backwards, it's a negative. So we can see we're going backwards and it's rapidly increasing. So our line is going to continue rapidly down, but in the negative as it's decreasing. As the screen gets further away, the change in distance starts to increase slowly. So it's increasing slowly until it reaches -1. So it's going to slowly reach -1. So now let's imagine we are hanging the screen underground. Let's make this into our circle. The distance of the screen slowly decreases to start with. So the distance of the screen from this point to this point is just slowly beginning to decrease. Now as we get closer to 0, it rapidly decreases. So remember, the distance between this point and this point is much greater than this point and this point. So we started slow and then we rapidly increased until we reach our 0 distance. So to finish off our revolution, once the screen is at a distance of 0, it begins to rapidly increase in distance. So as we move it, rapidly increasing. So we can continue this in our positive direction, rapidly increasing. And as the screen gets further away, it reaches a distance of 1. So here we have 1 revolution. So how do we compute this percentage? So we want to divide the current value of the distance of the screen by the maximum value, which is the radius. So looking at that, we have a certain distance, an angle theta, and we have our radius 1. So our distance of our screen across the ground divided by our radius. So the distance of the side closest to the angle, so here's our angle, and this is our closest side. That side is called our adjacent. So rewriting our formula, we get cos theta equals adjacent divided by our hypotenuse. So moving on to our last ratio, for today, we have our tangent. So we are going to now imagine that tan theta is equal to the height of a screen on a wall. So we're going to add in a wall. So this is our wall, and what we're going to do is we're going to hang a screen from this wall. So if we draw that out, here we have the height of our screen, which is our tangent. The height. And here we have our radius, which is 1. So our tangent of theta can be written as tan theta equals the height of screen. So let's notice a few things about the tangent. It starts at 0, and it starts increasing at a height slowly, and then it rapidly increases until it reaches infinity. So let me show you how this works. If we start with a height of 0, let's draw in our wall. So we have our height of 0. We're going to start at 0. So as we change our angle of our screen, you can see that the height of our screen slowly changes until, oh, I ran out of space. So it starts slow and then it rapidly increases. So if you imagine these lines continually going out until it reaches a vertical, which is infinity. So this starts off slow and then rapidly increases until it goes to infinity. So if we draw a wall on the other side, so a tangent on the other side of our dome, we're starting at negative infinity. So we're going to start down here. So this is negative infinity. And we can see that we're going to rapidly decrease and then slow down. So if these continued out to our wall, you'll see that it's quite rapid and then it slows down. So we're going to start with a rapid and then we're going to slow down until we reach, until we approach the tangent of 0. So here we're at 0 and here we're at 0. So again, we can imagine hanging the screen on the wall underground. And because we're looking underground and we're backwards, the two negatives are going to make a positive. So we're going to continue drawing in this positive quadrant. So from this point, we're going to slowly increase the height of our screen, and then it's going to rapidly start getting bigger and bigger until it reaches infinity. So we start off quite slow, and then we rapidly increase until we go to infinity. And lastly, we want to finish our circle. So we're still underground, but we're moving forwards. So we are going to be in the negatives because we're underground, and we're starting at infinity. And you can see that at infinity, and we're going to be rapidly decreasing until we slow down. So rapidly increasing until we start to slow and we reach 0. And one revolution is then complete. So drawing this out, remember we have our wall, which is our tangent. So the height of our screen at some angle, theta, with a radius of 1. So tan theta is going to equal to the height of our screen, which is on the wall, divided by our radius. So we already know that this length can be rewritten as the opposite, as it's the furthest away side from our angle, and the closest side to our angle is our adjacent. So this is where our first 3 trigonometric ratios come from. And here is a summary of our formulas. So we have sine theta equals opposite over hypotenuse, cosine theta is equal to adjacent over hypotenuse, and the tangent of theta is equal to opposite over adjacent. Thank you for watching.